Hi, Algebra 2, Day 4 notes. Before we jump into the packet, I just wanted to do a quick warm-up with you. Feel free, you don't need to write this down. I just want you to watch for a moment. So super simple. The start is if I give you the numbers 1 through 10, so the natural numbers here. If I ask you what's the probability of picking an odd number, and then what's the probability of picking a number divisible by 3? So what I want you to think of is, all right, probability of picking an odd number is, what are the odd numbers? So we got 1, 3, 5, 7, and 9. And so that would just be 5 out of 10, right? Easy, or 1/2. What's the probability of picking a number divisible by 3? Well, of the list, we've got 3, we got 6, and we have 9. So if you can think about what's in the set itself, it makes it really easy to answer the question, all right? And then that particular one wouldn't reduce. The reason I bring that up is because when you look at the note packet, it says from the warm-up, but it gives you what's called a condition in the probability that it's asking about. So I'm going to slide the note packet underneath now, and I want to think about this. From those same set of numbers, what's the probability of picking a number divisible by 3 given that it's an odd number? All right, so in that case, when we say given that it's odd, it's got to be an odd number first, and then what's the probability that it's divisible by 3? So when you think about all of the odd numbers, and we just listed them a moment ago, 1, 3, 5, 7, and 9, what's the probability it's divisible by 3 given that it's odd? Well, there's 2 of them there. But now it's not out of 10 because given that it's odd, there's only 5 numbers that are odd. So that would be 2/5. All right. Then when it says, what's the probability that it's odd given that it's divisible by 3? In this case, it's got to be divisible by 3 first. So that's that second set we just looked at. Whoops. Where it's 3, 6, and 9. So given that it's divisible by 3, what's the probability that it's odd? Well, there's 2 choices here out of those 3 numbers. So this would be 2/3. So when we see things given that this or given that this is happening, that is referred to as conditional probability. So given this condition, now what's the probability that it's happening? So what it ultimately does is it creates a small little subset within that bigger set and then says, all right, now that you're in that group, what's the chance of this happening? So when it says, these are examples of conditional probability, well, we got that right there. So the definition, right, is that the probability of an event occurring given, that's going to be a key word there, given that another event occurs first. So the other event, like in this first case, was it was odd first, then what's the chance it was divisible by 3? Now, there's a couple ways to calculate this. So when we say probability of A given B, what it's actually equivalent to is the probability of A and B. So you have to have both of those things going on. But you have to divide it by the probability that it was in that given set in the first place. So divided by the probability of B. Now that's using words. If I change this notation to say, okay, how does the symbol read? Well, the symbol for the given is going to be a vertical line. So it's going to be A given B, like that. And then it would be the probability of A intersect B like that, and then divided by the probability of B. So what goes in the denominator? It's always whatever that second detail was. Whatever was given, that's what's going in the denominator there. So if we were to change it around and do B given A, the top would be the same, but the denominator would then turn into the probability of A. So let's see how this actually works, all right? So I'm going to slide this up just so you can see a little bit better. There we go. All right, it says use the conditional probability formula to calculate them now. So the probability that it's divisible by 3, given that it's odd. All right, the divisible by 3 is like the A part of it. Given that it's odd is like the B part of it. So what we're saying is that the probability would be equivalent to A and B. so it's got to be in both sets. It has to be in the intersection, over the probability of the second part, the odd part of it. Oops, I just realized I wrote that two different ways. Let's make this a little bit easier. Let's go. Let me readjust up here. So I'm going to say the probability that's divisible by 3 and odd divided by the probability of the B part that it's odd. Okay, there we go. Maybe that makes more sense. All right, so now let's look at the whole list. If I look at 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, I squeezed them all in there. All right, divisible by 3 and odd. So 3 is divisible by 3 and odd. 9 is divisible by 3 and odd. So there's those two values to pick from. Divided by the probability that it's odd. All right, well, how many things here were actually odd? All right, that would be, oops, that was 2 out of the 10. Probability that it's odd was 5 out of the 10. And then when you're dividing by the same thing in both cases, those 10s are going to wipe right out, and you end up with 2/5. If I rearrange the way the question is given, find the probability that's odd given that it was divisible by 3. So the probability that it's odd given that it's divisible by 3. The numerator doesn't change because it's still going to be odd and divisible by 3. It's kind of like a commutative property. It doesn't matter the order in which you say it. You still get the same numbers in the overlap. But in this case, the denominator is now the probability that it's divisible by 3. So the numerator would still be 2 values out of the 10 that are odd and divisible by 3. The denominator, well, how many values are divisible by 3? Just 3, 6, and 9. So 3 out of the 10. And then again, the 10s go, and there's the 2/3. Right? So the rule works. The reason you would need to know the rule is it depends on how the information is given to you. So this next example is a perfect showcase of that. So when I slide on up here, it says we got the probability of some generic thing A is 0.45. Probability of B is 0.35. The probability of A and B or A intersect B is 0.10. Okay. Find the probability of A given B. So first, it's just saying write it in proper notation. All right, so the proper notation, probability of A given B. So you're using that vertical line right here. Now to calculate it, well, use the rule that we just wrote above. So I'm going to write it one more time just so that it's on the screen with me right now. It's the probability of A intersect B over the second piece, the probability that B is happening in the first place. All right, the intersection, that was the 0.10. Probability of B is the 0.35. So do we ever end up using the 0.45 in this case? Nope. So you had to decide what parts you needed. Don't be surprised if you have a little bit of extra information sometimes. All right, then from here, grab your calculator, 0.10 divided by 0.35. Go ahead and math frac that baby. And it comes out to be 2/7. So that's the chance of the probability that you would pick whatever A is given that B has already happened. Okay, so formula is not hard to use, but definitely make sure you write it down so that you can use it, on the homework and things tonight. All right, on to the next page. We got a couple different examples. Some of these ones will go kind of quick. So this one, given, there we go. Given the probability of B given A. All right, so they're giving you that new stuff. And the probability of P and A is 0.6. Find the probability of just A. All right, so all this is trying to show is that if I know this formula, I can kind of plug in anywhere I need to and solve for the missing piece of it. So what I mean by that, probability of B given A, that's the same as B and A on top, which is the same as A and B. Don't forget, we just said that that's commutative, so I could put B here and then A or vice versa. But what matters is in the bottom goes the probability of the second part of A. So that's the rule. Now I want you to plug in the parts that you know. I know that this part on the left is 0.85. I know on the right that the numerator is 0.60. I don't know what the denominator is, so you can call it X or you can call it the probability of A. Hold on one second. Yes, Gracie, what do you need?
Jade's in her yard.
Oh, well, I can't worry about it right now. Thank you, lover. Our neighbor's dog loves our yard now that we have a puppy, so My Gracie girl was letting me know. All right, let's cross multiply. We get 0.85 times the probability of A equals 0.60. And then you're going to divide both sides by that 0.85. And so if we take 0.60 divided by 0.85 and then math bracket, the probability of A would be 12 over 17. So it's just like any formula. You can plug in, rearrange, and solve for the part that you're missing.
Go home, Jade.
Oh, now she's trying to encourage her to go home. Well,
Jade, go home.
sometimes it works. All right. Let's see. Let's take a look at this next one. So given the probability of M is 0.72, probability of T, and we don't know what these are, they're just kind of generic, and then the probability of both of them, so M and T, determine each of the following. All right. So this is just practice with the rule. You're going to have it down by the end of this. So when it's T given M, that's equal to probability of T and M in the numerator divided by the probability of M. The second one is what goes in the denominator. Whereas the one next to it, you're going to have the same numerator, because whether you write M and T or T and M, it doesn't matter. But the second piece is the T, so it's going to be over probability of T. All right, let's calculate. That's going to be 0.23 in the numerator for both. In the denominator of the first one is going to go the 0.72. The denominator of the second one is going to go 0.24. Right. So if we actually calculate and clean these up, this one's going to come out to be 23 out of 72, but it's about 0.319, all right, approximately. 23 out of 24, if I just move those decimal places, all right, that's going to be about 0.958, right? So the whole reason I leave it as a decimal and don't really worry about it too much is it just asks, do they come out equal? And it should be really evident that no, not at all right? Which means this is not commutative. All right. So the idea of the and piece of it, yeah, that's commutative. But the actual, T given M or M given T, that is not commutative. The order matters, all right? So not equal. So make sure and pay attention to what the second part is, because that's the part that goes into the denominator. Okay. For the next example, we've got a chart. It looks similar to one I think we did yesterday in the notes, where it has the number of males and females going to college or not going to college, and then all the totals. So 29 total kids going to college, you get it. 23 total not going to college, 52 total that they actually interviewed here. So when it says determine the following probabilities, first three, quick and easy. Probability of picking someone who's a female. Total females, that's 22. Out of the total number here would be 52. And now we can reduce it. I'm not even going to bother at the moment. I'm going to leave it alone. Probability of F and C. So this is the intersection. So look at where they overlap. So female going to college, that's 13 right there. So that's going to be 13 out of 52. Probability of going to college, that's the total in that column. So that's 29 out of 52. All right, here's the newest one. Probability you're going to college given that you're a female. All right, you can do this a couple of different ways. We can use the rule. So the rule would say it has to be the probability of both and then divided by the probability of the second one. So I can look at it that way. I can say the probability that you're going to college and you're female. So that was the 13 out of 52 from right here. Divided by the probability that you're female. That was the answer we got from part A. That was 22 out of 52. All right, and then here's another case. 13 out of 52 over 22 out of 52. Those 52s are going to go. And we'd get 13 out of 22. Right? Something I want to point out, though, when it says in part E, is there an easier way to get the answer just using the table? Well, it's saying the probability that you're going to college given that you're a female. If we look at the female column as our little subset here, there's 22 total females. So if I just look at that column, we're saying if you're in that column of being female, what's the chance that you're going to college? Well, 13 of them are going to college out of 22 total. And there's the exact same answer we just got a moment ago. So you can just look at the chart and say, all right, let me just look at just the females and then consider how many of them are going to college. It's a little bit simpler to read it that way, but you can use the rule if you like the rule. All right, we got just one last page to look at. I think my posted notes on the website might even have an extra page, so have fun with that. But you obviously, if you're taking notes along with me, you don't have to worry about that too much. I just didn't want you to think that you were missing a page in your packet. You're not. It's fine. All right. Last page here. It's saying in a certain class of students, 27 students, you got the data in the Venn diagram. So those that have brown hair, those that have blue eyes. This is just stands for the whole set of students. And then there's 4 people that fall outside of that, meaning they don't have brown hair and they don't have blue eyes, so they don't fit into either. All right. Find the probability that someone has brown hair given that they have blue eyes. So I want to take the approach of what we did the last time. I want you to look at just this little subset. So if you're in the blue eyes circle, if I ignore everything else and I just look in that blue eyes circle, right, it's saying, what's the chance that you have brown hair? So with being within the blue eyes circle, there's 1 person there that has brown hair out of the 9 people total, because you got to put the 8 and 1 together, that have blue eyes. So this would be 1 out of 9. Mm-hmm. It says find the probability that a student chosen at random has blue eyes given that he or she has brown hair. Well, that would read the opposite. So blue eyes given that they have brown hair. So look for that word given, and then you know that this is your setup. So in this case, I need both, but then you're dividing by the brown hair part of it this time. So the both would be the 1. The brown hair part, I've got a total of 15 people there. And there you go. All right. And if you cover it up, it should hopefully make sense. Yeah, there's 15 people. What's the chance that you have blue eyes given that you're in that brown hair circle? Well, just 1 of you. So there you are. All right. The last part. It says the formula for conditional probability is B given A equals both of them divided by the probability of A. And it says solve this formula for the probability of A and B. All I mean is just rearrange the formula. That's all we're asking to do here. So if we think about like throwing this over 1, you can cross multiply and we can say that the probability of A and B is equal to the probability of A times the probability of B given that A has happened. All right. And now if you think about that and you're like, wait, what? And loosely turns into you're going to multiply over here. So when I see the word and, it's going to translate to multiply. If you look at what we're doing, we're multiplying the probability of A times the probability of B. The only difference is, does A happening, change this at all? Right? So it says we say 2 events A and B are blank if the following is true. And in this case, if the probability of B given A equals B and the probability of A given B equals A, we would say that they are independent. Now, it looks a little wordy at the moment, but what that means is they're saying the probability of B, given that A has happened, is just the same as B all by itself, meaning that A had no effect on it. And if the probability of A, given that B has happened, is the same as just the plain old probability of A, means that B had no effect on it. Right? So like, what's the probability you're going to pass your math test given that there's a storm out in California? It's probably not going to change any. Like that second event is probably not going to affect the first one at all. So they would probably be independent events. Like they don't have any bearing on each other. Right? So when it says interpret what the definition of independent events means in your own words, you can write it down however you want, but basically something to the effect of getting across that, the events do not have any impact on each other. Or one event happening does not impact the other one. Okay, hope that helps. Days 1 through 4 are due tomorrow. There is a Google Meet on Wednesday. If you have any questions and would like to hop on and ask.